The third part of this Friday lecture is about analytic functions. So these are functions that can be expressed by power series and give a nice context to talk about uniqueness in a different way, and in an even stronger way. And give a nice context to talk about analytic function, a power series, and uniqueness, and they lead to an application of connectivity to uniqueness. So what is an analytic function? An analytic function is a function on some open set of R, and it's analytic if for every point inside that open set, we can, in a neighborhood, express f as a power series. And this has to be defined on the whole interval, so have a radius convergence larger than epsilon, where we're claiming equality. So pictorially, what we are looking at is that we have some set where things are defined, often an interval. And what we insist is that for every point x0, we have some radius where we can express the thing as a power series. And the crucial thing here is that if you choose a different point, you will get a different radius and a different power series. But we insist that these different pieces fit together in one big function. And that this kind of an expansion can be done at every point that we might want. So even other points in this picture. So it's kind of hard to show that something is analytic, and usually you have to use something like Taylor remainder theorem to get there. But since I don't want to cover that, the only example I will give is this very simplistic example, 1 minus 1, 1 over 1 minus x. And this is actually an important example because it has a nice trick about geometric series. Remember that this is not defined, obviously not defined at 1, it blows up at that point. But what you normally do is that, okay, if x0 is 0, so if you're centered at 0 here, then you have the familiar power series that converges up to 1. So all x's such as that value is less than 1. So it's just given by f of x is equal to x to the n. And this has radius of convergence 1, basically following what we did on Monday's lecture. But suppose we have some other center x0, not equal to 1, generally. Not equal to 1. If it was equal to 0, it would be covered by that case. And at 1, that's outside the domain of our function, so we don't have to verify analyticity there. So we want to find a power series in powers of x minus x0 that is centered at x minus x0. So what we do, okay, we want to force the x minus x0 expression in there. So we will subtract and add, but add it in a funny way, the x0 here. So now we have a thing like x0, but we want to get it a little bit cleaner here so we can still use the geometric sum formula that we know. So we'll divide the denominator by 1 minus x0, pulling that factor out. And this then leads to 1 minus something given by a fraction of two things. So let's think about this as y here for a moment. What we'll do, so this is 1 over 1 minus y for a weird y. So it can be expressed as sum n equals 0 to infinity of y to the n, as long as y absolute value is less than or equal to 1. And that y is here. So, but let's see what we get from here. If we reorganize the factors, so pull out the x minus x0 to the n, and the other factors, so 1 over 1 minus x0 to the n plus 1, then we get the power series representation that we would like, namely here we have our coefficient an, which is equal to 1 over 1 minus x0 to the n plus 1. And this series converges, it's can be verified directly when y has absolute value less than 1, or when x minus x naught has absolute value less than 1 over 1 minus x naught. That's when all of this was valid. So the radius of convergence is at least 1 minus 1 over x naught. By theorem, if you take the nth root of this expression, you will also get that r is actually equal to 1 over 1 minus x naught. There's a typo here. No reciprocal. Okay, so we get a power series, and it had involved this nice trick of adding and subtracting and taking a factor. So, but notice how for different x naught you get a different radius and different coefficient. Yet these all these power series, they fit together to create this function. So even if you are at -1, the power series at 0 stops to converge, but you can start a new power series at that point, representing the function in the neighborhood of that point. You can continue this game until infinity. But this leads to an interesting possibility. Suppose you have something analytic, and it's defined on some interval AB, and it vanishes on a part of that interval, and we say that it vanishes everywhere. So we have I, we have some interval within it, J, along which the function is equal to 0. Can we extrapolate from that interval? Can we conclude that actually f is equal to 0 everywhere, and that the coefficients of all power series are equal to 0? So we'll see an example how this, in general, for continuous functions or piecewise functions, you usually cannot go from the information that the function is 0 somewhere to that the function is 0 everywhere, but analytic functions are special. And they have these special uniqueness statements that we used. And the proof here, even though the statement is a little abstract, actually it involves only things that we've seen so far, and connectivity is the main tool. We want to show that the function is equal to 0 everywhere. So what we will do, we will define a set of points which correspond to f being 0, but we'll do it in a funny way. So we'll take all the points such that f of x is equal to 0, but a little bit more, that f is equal to 0 in a neighborhood of that point. So x minus delta, x plus delta is equal to 0. We do this because we need in this definition a little bit of room to work with power series. So, but let's see. We will show that this set is everything, and that will require showing 3 claims: non-empty, open, and closed. And as you remember, the only non-empty, open, and closed set in I would be the whole space. And if everything is I, then that means that you are 0 everywhere. So it's enough to show these 3 things by connectivity. It seems like we've gone quite far from the problem. We were still analyzing a fixed set, but by connectivity, this is permissible. So A is not empty. Usually this is rather obvious. Well, there is some interval J such that that is in I. So if x naught is in J, and delta positive is such that x naught minus delta, x naught plus delta is contained in J, well, this is possible because the set is open, interval is open, then we know that x naught is in A because f restricted to J is equal to 0, and therefore restricted also to the subinterval of that. Now openness is basically exactly the same. If x naught is in A, then that means that there exists a delta such that f restricted to x naught minus delta, x naught plus delta is equal to 0. But if y is in x naught minus delta, x naught plus delta, we can set a delta y to be equal to delta minus x naught minus y. And then what we have is that y minus delta y plus delta y is contained in x naught minus delta, x naught plus delta, and therefore f restricted to y minus delta y plus delta y is equal to 0. So y is in A, because A consists of exactly those points for which there exists a neighborhood where the function is equal to 0, and we identified a neighborhood where the function is equal to 0. So the set is open, non-empty, and open. So next we have to show that it's closed in I. So then in I, remember, I is an open interval in this problem, so you have to talk about the relative topology. But closed in some space means that if we want to show that if xn are a sequence of points in A that converge to some x in I, then x is in A. Well, there are two cases. Either there exists an n such that xn is equal to x. Well, in that case, because xn is in A, then x is also in A. We're good. We want to show that x is in A. Okay, case 2, the interesting case, is that there does not exist such an index. So for all n, we have xn not equal to x. But f of xn is equal to 0 for all n. And f has a power series at x, because x is inside the interval where you are analytic. So we have a power series. So f of y, let's call this x naught so we can actually use x here. So f of x for all x is equal to sum of an x minus x naught to the n equals 0 to infinity. But this is equal to, so it has a power series at that point. But if we compare it to the other power series, which is just 0, so all the coefficients are 0, then by theorem, the uniqueness theorem, because we have that fxn equals gxn, we can therefore conclude that f is equal to g everywhere on the interval of convergence. And therefore, that gives us a neighborhood so that x naught is in A. This is exactly what we want to show. So we're using the uniqueness theorem to get us that interval. Therefore, by connectivity, the whole thing is the same. Now, what is the consequence of this? The consequence of this is that not everything has a power series. For example, the following function. That is 0 for negative values, and for positive values, it quickly grows to positive values. So how we obtain this is 0 if you are less than or equal to 0, and this weird exponential thing when you're strictly bigger than 0. Now, this cannot be analytic because f of, say, -1, 0 is equal to 0, f restricted to that set. But say f of 1, which is e to the minus 1, is not equal to 0. So this is not a non-zero function that vanishes on an interval. Therefore, it cannot be analytic. And the place where the analyticity fails is actually this meeting point. And this point, there will be no power series that will contain both of these parts.